In the previous video, we looked at how to use a trigonometric substitution to find integrals that involved the square root of a squared minus x squared. We're now going to use similar techniques for analogous functions involving the square root of x squared plus a squared and the square root of x squared minus a squared. Before we do that, we need to review a little bit about Pythagorean identities, which will be essential. So recall the standard Pythagorean identity is that cosine squared plus sine squared equals 1. And we can flip this around to get these two other familiar identities, that cosine squared is 1 minus sine squared and sine squared is 1 minus cosine squared. Less familiar are the identities that we get by dividing this top row by cosine squared. For instance, we have 1 plus, dividing by cosine squared gives us 1 here. Sine squared over cosine squared is tan squared, and 1 over cosine squared is secant squared. So just dividing this top equation by cosine squared gives us the identity 1 plus tan squared theta equals secant squared theta. And when we flip this around, we get these two identities. Secant squared theta is 1 plus tan squared theta, and tan squared theta equals secant squared theta minus 1. These last two identities will be essential for what follows. Dividing this top row by sine squared gives us a set of analogous identities for cotangent and cosecants. We won't be using these so much, so I won't dwell on them. Okay, so let's see how we use these identities to perform some useful trigonometric substitutions. Let's start off with the case where we have an integral involving the square root of a squared plus x squared. And let's just do an example. So let's try to find the integral of 1 over x squared times root x squared plus 4. So what we're going to do is make the substitution theta equals arctan x over 2. And this is because this then gives us that x equals 2 tan theta, which enables us to simplify this square root. When we do the substitution, we first have to find the relation between the differentials dx and d theta. By differentiating this second term here, we get dx equals 2 secant squared theta d theta. Now when we look at the square root term, the square root of x squared plus 4 will be 4 plus 4 tan squared theta. And that, of course, is 4 times 1 plus tan squared theta, and 1 plus tan squared theta is secant squared. So we can rewrite that as 4 secant squared theta, and the square root of that will just be 2 secant theta. So what happens when we put all this in? Well, we substitute in for dx, 2 secant squared theta d theta. That's the term on the top here now. And on the bottom, the x squared is 2 tan theta squared, so that's 4 tan squared theta. And this term, as we just observed, is 2 secant theta. So we can cancel one of these secants out and the 2 out, and that leaves us 1/4 the integral of secant theta tan squared theta. Well, this is still not an easy integral to do, so let's rewrite this integrand in terms of cosine and sine. So secant theta over tan squared theta, secant is 1 over cosine theta, and tan squared theta is sine squared theta over cosine squared theta. So that's cosine theta over sine squared theta. When we multiply the top and the bottom by cosine squared, it simplifies to this. Now this is something that we can integrate with an easy substitution. Let's see how to do it. Okay, so just to recap, we've got to this stage. We did our substitution, we got this, and then we did a little algebra to see that this integrand is equal to cosine theta over sine squared theta. Now we notice that the top here, cosine theta, together with d theta, is the differential for the substitution u equals sine theta. And so This will give us an easy form for this integral. The integral of cosine theta over sine squared theta. The cosine theta d theta part becomes du, leaving us with just a sine squared to deal with, and that's just u squared. So this whole thing becomes 1/4 the integral of 1 over u squared du. And we know the antiderivative of 1 over u squared is minus 1 over u. So that gives us a final answer of, when we substitute back for sine theta in for u, we get minus 1 over 4 sine theta plus c. And finally, we can rewrite that as minus cosecant theta over 4 plus c. But we're not finished yet, because we need to get this back in terms of theta, back in terms of x. And remember, our substitution was x equals 2 tan theta. So we need to know what cosecant theta is if x is 2 tan theta. Well, we can do that using an algebraic identity, but another way of doing it is to construct a triangle with angle theta and such that the tan theta is x over 2. Well, since tan theta is opposite over adjacent, we just have to construct a right angle triangle whose opposite side is x and whose adjacent side is 2. That'll look like this. Then the hypotenuse by Pythagoras' theorem is just the square root of the sum of the squares of the two sides, which is x squared, the square root of x squared plus 4. So then cosecant theta, cosecant is 1 over sine, and sine is opposite over hypotenuse. So cosecant is hypotenuse over opposite, which is the square root of x squared plus 4 over x. So this enables us to substitute back for cosecant theta and get our final answer of minus root x squared plus 4 over 4x plus c for the integral of 1 over x squared root x squared plus 4. So there are many similar problems like this that can be solved by the substitution x equals a tan theta. They all reduce the problem to a trigonometric integral, for which one has to use the techniques that we've learned earlier to do trigonometric integrals involving tangents and secants. And then the final stage is to substitute back this trigonometric answer we have for this substitution to get an answer in terms of x. Let's move on and look at an example of the other kind of substitution that we want to discuss. That's integrals involving root x squared minus a squared. And so let's do a simple version of this, the integral of 1 over root x squared minus a squared. So for this, we're going to use the substitution theta equals arcsecant x over a, or more familiarly, x equals a secant theta. So the differential in this case will be dx equals a secant theta tan theta d theta. And this square root, x squared minus a squared, is the square root of a squared secant squared theta minus a squared. So that's a squared times quantity secant squared minus 1, and secant squared minus 1 is tan squared. So we replace that, the term inside the square root, by a squared tan squared theta, and then the square root of that is a tan theta. So going back to our original problem, the integral of 1 over root x squared minus a squared will convert to putting in the differential, a secant theta tan theta d theta, and then substituting for this bottom term, that's just a tan theta. So we get this picture that the a's cancel out, the tan thetas cancel out, and we get secant theta. So we end up with log secant theta plus tan theta plus c. And then the next stage is to substitute back to get x. Secant theta is x over a, and tan theta is root x squared minus a squared over a. We can also do that using the triangles as we did before. To do that, if we have secant theta equals x over a, this is going to be the hypotenuse divided by the adjacent side of our triangle. So we'd make a triangle with angle theta, hypotenuse x, adjacent side a. By Pythagoras' theorem, the opposite side is root x squared minus a squared. And so tan theta being opposite over adjacent is root x squared minus a squared over a, which is exactly what we observed algebraically in the previous slide. So putting this all together gives us our final answer, that the integral of 1 over root x squared minus a squared is log secant theta plus tan theta plus c. So that's log x over a plus root x squared minus a squared over a plus c. So that's an answer. It's not the standard answer for this indefinite integral. So let's just see how we can play around with it a little bit to get to a more familiar form. So we were at this stage here. Notice that we can put this over a common denominator of a. Then we have the log of a quotient. The log of a quotient is the difference of the logs, so it's log of the top minus log of the bottom, log a. And this term here, which is a constant plus an arbitrary constant, can be replaced by just another arbitrary constant. So if you look in an integral table, you'll find that the integral of 1 over root x squared minus a squared is usually written as natural log absolute value x plus root x squared minus a squared plus a constant. So let's summarize what we've learned in this and the previous lecture. So here's a table of substitutions that you should use to find integrals involving these kind of square roots. If the square root is a squared minus x squared, you use the substitution x equals a sine theta. If it's square root of x squared plus a squared, you use x equals a tan theta. And if it's square root of x squared minus a squared, you set x equal to a secant theta. So this is a pretty good general rule that takes out any of the guesswork involved. Unfortunately, there are a few exceptions to this. Not that the technique won't work, but there are some situations where you certainly wouldn't want to use a trigonometric substitution because there's a much more obvious direct substitution. So let's have a look at an example of this, the square root of x times square root of 4 minus x squared. And hopefully you can see there that the substitution u equals 4 minus x squared solves this problem very quickly. Du is minus 2x dx. So the integral is, well, x dx converts to minus a half du, and the square root of 4 minus x squared converts to square root of u. So this is just a power, x to the half, u to the half, so its antiderivative is u to the 3 halves times 2/3, and so we end up with the answer minus a third, substituting back for u, 4 minus x squared to the power 3 over 2 plus c. So one should check before going ahead with a trigonometric substitution that there isn't a more direct way of solving the problem. However, using the trigonometric substitution will almost always get you to the answer eventually.